exercise 45. This is a follow-up of exercise 44. So recall exercise 44. We characterize the length preserving linear transformations in R3. So denote this set of 3R to be those linear transformations R3 that preserves tensor products. Preserves dot product, dot product. In particular, you could also say same as preserved distance or length. And in particular, so such a linear transformation would be invertible because it preserves length will tell you it is 1-to-1, which means it's injective, because if the image has length 0, then the pre-image has length 0, and so, which means the pre-image is 0 vector implied the image is 0 vector implied the pre-image is 0 vector, so the kernel is 0, so it's injective. And for matrix transformation, that is square matrix, which means which means a homomorphism over vector space. It is injective implies it's surjective and bijective. Okay, and so this is invertible. So we characterize this by using its representing matrix, the same as saying this matrix satisfies M transpose M equals identity, which is more transparent in some sense. Okay, and the remark is that all those have down in exercise 44 actually it works for, instead of n equals 3, but for arbitrary n. Because, so let me first write down, we still denote this to be dot product preserving linear transformation. Preserve dot product. Okay. So I'm claiming that Rn dot products preserving is again equivalent to just a binary matrix such that transpose M equals In. So let's quickly recall the idea. So firstly, a quick remark is that this is again equivalent to say that M has orthogonal columns. Simply because if you write M as column vector u1, u2, un, then this is just ui transpose matrix multiplication uj for ij, which is also the same as ui dot product with uj for nj. So this equals identity matrix if and only if the form orthogonal basis or orthogonal columns. And exercise 44 show that this characterization, the same method show that is equivalent to it preserves dot product for whatever u, right? So one direction is obvious. Sorry, so for the other direction you use test vectors. So which means this direction is very easy just by computation. So suppose your M is like this, so mu, let's write u is its coordinates u1, u2, un. So to avoid this confusion, let me just write x1, x2, xn. and then dot product with MV. Let's say V has coordinates y1, y2, yn, and then just by the linearity. So first you compute what is matrix multiplication. This is just summation xi times ui. Let me write the arrow to denote the column vectors of M. This comes from the matrix multiplication of a matrix with a column matrix, right? This linear combination of the column matrix of this matrix. And similarly, this would be just yi ui, I from 1 to n, or maybe better written, replace this I by j, whenever this works. And if you satisfy this condition, so for example, you know that your m's column have orthonormal columns, then you could say this is exactly this xi yi, which gave you exactly this u dot product of its v. Or if this notation is better to, instead of writing u and v, maybe you could write x and y. Maybe it makes this notation more consistent. I mean, you could write x, y, and then this is finally equals x, y, for any x and y. Let me think, if you want to start here and directly show this then you could also say, yeah, you just use this. You could also make the computation even light. So this is just an x transpose matrix multiplication with my, and so this is x transpose m transpose, and then my, but you know m transpose m is identity. This is x transpose y, and so which is x dot product with y. Okay, or you could use this, or you could just use their computation. So whatever, this direction is very easy, and the other direction we use test vectors, right? We use test vectors. Our test vectors are u. Let's pick u equals ei, standard vector. V equals ej, and then you will say that this is telling you that I transpose m transpose m or ej equals ei transpose ej. And then this is telling you that each entry of this, let's call this entry, let's call it mij. Mij would equal delta ij, so which tells you that this is the identity matrix. So I'm almost repeating the proof, exercise 44. But now let's see what we want to do here. So exercise 45, we want to show that firstly, this is not only a set but a group with respect to matrix multiplication is a group. Secondly, show that the determinant is always plus or minus 1 for M in this group. Okay, and we call this group orthogonal group of degree n over the real numbers, and this subgroup consisting of those determinant equals 1 special orthogonal groups. So to prove this is very quickly, so let me write a sketch in. So firstly, identity matrix is there. If you have two matrices in this set, then the multiplication is again there. So you could just do the computation just quickly, and I would say even without computation, you would say it corresponds to the linear transformations. Let's still denote that linear transformation. Let's denote the linear transformation TM1, TM2. So the linear transformations are length preserving, and so the composition of the linear transformation is again linear transformation length preserving, which corresponds to the matrix multiplication of the matrix. And then finally, if you got M in this set, and then show this M is invertible, and its inverse is again there. For example, actually, as I said, once you are square matrix and you are dot product preserving, you are injective, and you are surjective, and you are invertible. And you can also argue that the observation of the characterization from the definition already implies by my remark that the column vectors are also normal. But actually we don't even need orthonormal. We just need a linear independent. Square matrix or whatever matrix with linear independent columns would add linear transformation, being an injective linear transformation. And so in particular, in the square matrix case, this corresponds to a linear transformation over a vector space itself, so a homomorphism over this vector space, which is injective, and that would imply it's surjective because it's finite dimensional vector space, and invertible. Moreover, this M inverse would just be its transpose. And so we're left to check whether the transpose is ORN, but this is just direct computation because what you got is M transpose M equals IN, implies taking transpose on both sides, M transpose what I want to say is, knowing this, what you want to check is that is simply M transpose and transpose and M transpose equals I. That's what you want. But this is just M transpose equals I. This is the case because M is invertible with its inverse M transpose. Secondly, let's check this determinant works. But firstly, notice that the determinant of identity is 1, which is also by your characterization of orthogonal group. So now we have proved this is a group. Okay. So any element from the orthogonal group, let's call it orthogonal group. satisfies M TAM A equals identity, so its determinant satisfies this, but the transpose of the determinant of the transpose is the same as determinant itself. So SDP, so just by the definition, that would be, so basically the determinant take all the possible multiplication of elements from different row and different columns. So you could also say use cofactor expansion, so the determinant could be computed by a cofactor expansion along arbitrary row or column. So cofactor expansion along the first row of M corresponds to cofactor expansion along the first column of its transpose, so they give you the same result. And so this implies the determinant is plus or minus 1. And so we could check, or directly there's those with determinant positive 1 will form a subgroup of all those orthonormal transformations. By definition, that those determinant equals 1. So in following exercise, we will even generalize this definition of orthogonal group. So basically, what we have introduced the orthogonal group is the orthogonal group with respect to the dot product. It's preserving the length comes from dot product. In general, you would say that you could describe a inner product of xy instead of, so let's say Rn, instead of a dot product, which is x transpose and then matrix multiplication with y, you will write middle multiplication with matrix A and then y. So the dot product corresponds to this A equals identity, but in general, inner products of Rn, which characterized by the axioms, not necessarily to be the case A equals identity. And if you, so we will prove this in exercise. So we classify all the possible inner products. All the inner products would be row matrix A, such that it is symmetric and positive definite, which means eigenvectors positive. Okay, we will show that in the following exercise. And what I want to say is that then instead of call the orthogonal group with respect to dot product, we could also define a general orthogonal group with respect to whatever inner products. In that case, the description is parallel to what we have constructed for orthogonal groups in this exercise. So instead of M transpose M, let's still call it O maybe. I don't know what a good notation for this orthogonal group, to avoid making things confusion. Let me just call it orthogonal group Rn with respect to this inner product will be M transpose A, M equals A. We will show that this is the characterization to preserving So let me have a quick check. Am I saying something correct? So suppose you satisfy this. Are you going to dot product preserve, inner product preserving this one? So the question is M X inner product M Y. So that would be let me check this. Oh, make sure I'm not saying something wrong. So mx inner product my. By definition, this would be mx transpose a my. So this equals x transpose m transpose a m y, and so this is x transpose, and then there comes this term. So we require this to be a y, and so again this is the inner product of x and y. So again, indeed, if you require m transpose a m equals a, this implies that this matrix transformation preserves the inner product, which is given by this. Okay, and question is, suppose you preserve this, would this imply this one? I think again this is more or less like you are using testing vectors. So some exercise. So suppose m preserves inner product. Would it imply M TAM equals A? So let's say, let's try to have a quick idea. Suppose, so what we have is basically here. This equals this for whatever x and y, right? Again, we are going to use test. So let's use x with ei, y with ej. Then what we have is eitm tam ej equals eita ej, and then again by computation, let's call this mij, call this aij. Then the left hand side will give you carve out exactly mij, and the right hand side will carve out aij. Let me think for a while. Yeah. Let me just make sure. because before what we done is when we take A equals identity, what we have here is identity matrix and the J. I'm just confusing a bit about this gave you just gave you delta ij. Right, this should give you just delta ij. It's suffices when A equals identity to show empty whatever here what equals identity, but if A is not identity, then would that really show this? A little confusing. Let me just check. Okay, so let me take an extreme example. Let's just take, for example, R3. Let me take E1 Ti and E3, then this would be 1 0 0 times identity, and then gives you 0 0 1, and so this is first row first column, first row second column, and then 0 0 1, and then this gives you 0 exactly. So basically you cannot directly conclude using this, I think. Let me think for a while. So I left this as a sub exercise.